Hello people, today I will make a Aspen Plus model of a Cascade heat pump. In Aspen Plus is a 2-stage and 2 refrigerant loop. And again, before starting the video, I assume you already know how a heat pump works and how a Cascade heat pumps work. I will explain very briefly. The goal for today's video is to model a Cascade heat pump with 2 vapor compression cycles, low stage and high stage, coupled with a Cascade heat exchanger. Here I will name it CHX, and I will quantify COP, compressor power, and key state points for high temperature heating applications. The model which I'm making today is based on this article. I will link this article below, and we will also check our results with some of the graphs. The model here is being made in, I think, in Python or MATLAB, not in Aspen Plus, and they are using different boundary conditions, which I will also tell the difference later. Let's describe the process description. So we'll start from point 1, where fluid will evaporate with the heat source. We assume heat source at 40 degrees Celsius. It will evaporate, and basically for compression it needs to be superheated, so I assume 2 to 3 degrees of superheating there. Then it will be compressed, and then it will be condensed, and then it will be isenthalpic expansion valve, and the cycle will be completed. And the heat in the condenser, which will be released, which will be rejected, will be used in the second loop, where different fluid will get evaporated, superheated, and compressed, and then reject heat via condenser, which will be useful heat. So we are assuming it around 120 degrees Celsius here, and here I will assume 40 degrees Celsius, and to cool it down to 25 degrees Celsius, like 15 degrees of temperature difference. And COP, coefficient of performance, will be the useful heat we'll get here, divided by the power required in both compression cycles. And working fluids used in paper are 134A, 1234ZE, and high temperature. Second cycle was R245FA and R1234ZEZ and R1336MZZ, etc. But for the baseline pair of this modeling, I will use in the bottom cycle 1234ZE, and for high temperature upper cycle R1233ZE. In Aspen Plus, I will use RefProp, and boundary conditions, we will come back to it later, but we are using T source 40 degrees Celsius, sink in first stage 60 to 90, in second 90 to 100, and these are some pinch temperatures which I may or may not use. Evaporator pinch, I think I'm using 3 degrees Celsius here. Condenser pinch, basically I'm using subcooling of 3 degrees Celsius there also, and heat exchanger pump also I'm using 3. Cycle assumptions, superheating and subcooling 3. Isentropic efficiency I'm using 0.8, in paper they are using 0.7. Expansion valve isenthalpic, and pressure drop is negligible for this, but I will also tell how it can or cannot modify. So let's start with first fluids. So you need to find out 1234ZE. Fine now. Yep. Add it, and then 1233ZD. Add components, add, and last is water. I think it's better to add water from there. I will name it ZE so that it will be easy to remember when we are modifying their values. In properties, we are using RefProp, yes, and then we'll go to simulation. To make our life easy, let's copy this file here so that we know what we are doing. And first let's change the unit. I like to use this kilogram per hour is fine, everything is fine, it's just with heat they are mentioning calorie per second, and I would like it in form of kilowatt and concentration also kilowatt, so that's fine. We'll use this new, and we'll start from the stream 1. I will name it stream 1, and then we will first use a simple heater. I will name it evaporator 1. This will be 2. As I mentioned, we need to mention streams here. Mole fraction 1, 2, 3, 4 Z, and I am first assuming just 1000 for the time being. Temperature I am assuming 22, let's say, or 22. And instead of pressure, let's go with vapor fraction. I will tell you why. Let's assume it 0.2. And now evaporator, and there also instead of temperature we use degrees of superheating. We said we'll use 3. And pressure drop, we assumed it's no pressure drop, so we'll use it 0. But if there is a pressure drop, you can just mention minus 0.01 or 0.02 and whatever value you are using, or you can use the actual pressure. But if you are using minus 0.01, it will just assume it's how much pressure it will be decreased from the actual pressure. We'll use E0, and then we can just run it. Yes, but as I always mention, I am always making the model flexible. So where is the heat source? So we have to use the shell and tube heat exchanger, but for the time being we are making our life easy. So I'm using another block. This is heat source. So heat source. There will be water in. We are assuming water is the heat source, and this is water out. And there mole fraction or mass fraction water. Mass flow rate, there we assume this will be the constant, this will be changed, so we assume 2000 kilogram per hour. Temperature of heat source was 40, and pressure, let's assume 1 bar. And we are assuming temperature will be cooled down to 25 Celsius and the pressure drop will be negligible. And now we run it, and we check how much heat is. So we have a 35 kilowatt is available, and evaporator is using 38. So we need to close the heat balance here. So one way is to just modify the mass flow rate until it will become 35, which will be time consuming. So what I will do, I will connect this heat with the input heat in evaporator 1, and I will name it heat 1, and then we'll exit one stream there. I will name it heat 2. I will just tell why this would be useful. And then we'll go evaporator back again, and we need to change the values again. That's fine. And now you go to design specifications, and there you name, let's say you name it heat evaporator 1. Double click it, and let's say what we want to do. we want to make this heat 0, because if this heat will be 0, then we will close this balance. So we'll select the heat duty, and heat 2 kilowatt is fine. So there you mention heat, target will be 0, and give some tolerance. I will give 0.001. And what we are changing, we are changing the mass flow rate of fluid. So mass flow rate will be such that it will only consume the heat which is available via heat source. And the better way is to use stream variable. Use stream 1, and variable is mass flow kilogram per hour. Just use some very high value so that it would be fine. So now you run your model runs fine, and now you see the heat is 35 and 35, and we used mass flow rate of 1000, but if you go to the results, mass flow rate will be a little bit lower than 1000. So now instead of 2000, let's assume you are using 5000 kilogram per hour of water, and you just run it again, and you see the heat is different. This heat is same, and mass flow rate, it will not be 1000, it will be significantly higher than 1000, 2268. Yes. Okay, and now again here also, as I mentioned, we are not using pressure, and we are using vapor fraction. And why we are using this temperature, basically this I will also change it via design specification block. I will tell you later, but let's just first close the cycle, and then we can modify it, because here we also do not know what are the conditions when it will come back from here. So it needs to match this equation, these conditions, but let's not think about it for the time being. Now we'll use compressor. I will name it compressor 1. Here, and material stream, this will be now stream 3, and compressor isentropic discharge pressure, and here we also do not know what is the discharge pressure required. Isentropic efficiency 0.8, mechanical efficiency I'm using 0.98. discharge pressure, let's assume discharge pressure is 25 or 20 bar for the time being. And now run the model again. That's fine, and we can check temperature and pressure. Temperature here is 86. So there we need a temperature of around 95, 96, 93, 94, because we are using here 90 degrees Celsius. So at least it should be a little bit higher than the temperature that will be used in the other evaporator. So one thing is, you can just modify the pressure, increase the pressure, decrease the pressure, and reiterate it again and again until you reach it. I am using 25 bar now. What is happening? And then you see now the temperature is 97 degrees Celsius. And other option is to just use another stream, dummy 1, use heat exchanger dummy, and then connect another stream, dummy 2, and connect this stream here. Now what you want to do is, here fluid is this, let's assume all flow rate is 1, temperature let's assume is 25 Celsius, and pressure is, let's assume you could say 25 bar, and there vapor fraction use 1 and temperature use 94 degrees Celsius. Then you run it and you check what was the pressure it shows there. It shows 27 bar. You can check it from the stream there also. It shows 26.84. So if I use 26, normally it will be around in this range there. There. Yep. It is not a right way actually, but just to give you a hint, because if you decrease pressure there, it will be 27, because here it is just making it in a saturation state, not in a superheated state, but in compression it's kind of a superheated state there also. So I think our pressure of 25 is fine there, but I will just keep it here for the time being. And now we'll use a condenser there, condenser 1. I will connect it. Stream name 4, and here we are using degrees of subcooling instead of temperature. Degrees of subcooling will be 3, and pressure drop again 0. And now for the last we will need a valve. I will use this symbol, expander 1, and I will just rotate it. And for the time being, we have another stream. I will just use it 1B, because and expander, we do not know at which pressure we need to expand it, but let's assume we are expanding it back to the 5 bar, and now we run it. So it shows we are consuming 25 kilowatt of power and providing 70 kilowatt of heat to the second cycle as a cascade. But we need to close it, and here again we check the vapor fraction is 0.58. I will just, vapor fraction is 0.58 after expander, but it is 0.2 that we were entering it at stream 1, which is not really right, and the cycle is not closed. So what I will do, I will delete this. I will connect stream 1 there, and then you need to go to the model analysis tool. No, you need to go to the convergence tier, and you need to mention stream 1 is recycled as a tier, and now it will converge, but again it will be fine. Now you see pressure is again 5 and temperature is 25, and which we are measuring 22, so pressure there should be 22. One option is to change the pressure in a way temperature here should be 22, but there is another easy way. Go to flow sheeting option, design specification, and use another. I will use pressure 1 because we'll do the same for another stream. So here we need to use T source and T fluid. So we have a first T source. T source will be temperature of heat source, and temperature of heat source which is being out. So it will be stream variable. Stream would be water out, and I need temperature, and fluid temperature will be inlet fluid temperature. So again stream variable, it was stream 1, and variable is temperature. And specification, so what we want T fluid to be T source out minus 3. So T source out is 25, it will be 25 minus 3, 22. And if we choose T source as 30, so it will be 30 minus 3, 27. So it will always have a 3 degrees of difference. So if a T source out will be 20, it will be 20 minus 3, 17. And tolerance, this gives 0.01. And what we are varying, what we are changing. So there we are changing the pressure of expander outlet. So now it would be block variable, and block will be expander 1 and variable will be pressure out. So here I am using 0.1 or 0.001. Don't give it a 0 into 40. And now you run it. You see it's converged. Now we can see the pressure there in stream, it's 22 and the pressure was 4.54. so even though we are mentioning it 5, but it's 4. And now I can show you. Let's say we are using, instead of 25 we are using 20. Just remember, now it's 87. Now we are taking heat source out at a lower temperature, so this value will be higher. So maybe these values will change. So I will reinitialize calculations. So instead of fluid temperature 22, now it should be 17. Okay, as you can see now, the amount of heat available from heat source is also high, so that's why it is adjusted accordingly. Similarly, when you change the temperature here back to 25, the value will be lower, and similarly the model will converge and model will adjust accordingly. So use of design specification is handy when you are doing calculations for different cases, and then you can run it from Excel or from some external Python code even also. Okay, see, the model has been run and now you see it is back to 87. Now we have to do the second cycle, which will be similar. Let's make it less crowded. We will need another heater. We will call it evaporator 2. And we will make new streams. We will call it 5 and here 6. Now I will make the model very quickly to save some time, otherwise the video will be very long. And here we are using R1234ZD. Temperature we will use 60 as we mentioned. Pressure, let's assume again 5 bar. We will change it with design specification block, and mass just put it 1 for the time being. And evaporator 2, again it will have a degrees of superheating 3, pressure drop 0, and again I will zoom it. We will close the heat balance from condenser to here. We will call it heat 3 and this will be heat 4. And okay, we need to do it again. And now with design specification block, now it will be easy. I will tell you a trick. Just copy it and then paste it, and then you need to edit ID. So now it's emit heat evaporator 2. Okay, but you need to change it here. And now instead of heat 2, the duty will be heat 4, which you want to close the heat balance. This heat 4, and spec will be same. And now you will vary variable from stream 5, this amount. Done. So yep, you run it and it will see 135 of condenser heat will be here. You can see the temperature 60 and 72, and here again instead of temperature and pressure, go for vapor fraction, use 0.2 for the time being, which will be adjusted accordingly later. And now compressor, we need pressure changers. Compressor, I will name it compressor 2, and then we need second condenser. Condenser 2, and we need second valve. Again go with pressure changer, valve, expander 2. I will rotate it, connect this stream here, new material stream 7 here, from condenser till expander. It will be 8, and this 5 will be connected it here. We have to go to tier and tell that our fifth stream is also recycled. With condenser, just use degrees of subcooling 2, 3, no pressure drop. Compressor again, let's assume it's 17 bar, because we need around a little bit more than 120 degrees Celsius, 125, so I just use 17 bar as first shot. But you can just do it with reiterating, or just check it again with this method as I told you earlier. And expander, for the time being, choose outlet pressure of, let's say, 5 bar. Yes, and go to design specification block again, and now copy pressure 1 design specification block, paste it, edit ID 2, OK, and then press OK. And it will be same, but now you change the variables. So I will, what you need to adjust, we need now the T source will be stream 3 and stream 4. So stream 4 is out now, so here it will be stream 4, and temperature of fluid will be stream 5. So the temperature of fluid must be 3 degrees lower than source temperature. So if source temperature is what is temperature? Source temperature is 87, so here it will be 84 something. Yep, 84 something. And how we are varying it? We are varying by changing the outlet pressure in expander 2. So we will run it. It will give an error. I know why the error comes. I think here compressor has some liquid there, so you need to change the convergence to vapor liquid. Run it again. Yep, it will not give any error. I will just reinitialize it and then run it, the whole model again. Yes, everything is intact. Yep, so outlet we are getting 159 kilowatt of heat, and we are consuming 25 kilowatt from compressor 2 and 48 kilowatt from compressor 1. We can see the temperature. Yes, temperature of compressor 2 is 125, we were right here, and pressure is not 5 as we shown, put it here in expander. Pressure was adjusted to 7 bar as we saw in our design specification. We can just check there also, pressure 2 results, so manipulated it to 7.3 bar. and vapor fraction is 0.33, even though we were mentioning is at 0.2. So this is how you make the model flexible, and we can also check the sensitivity analysis and we can see some results. Let's go back to this paper. They are using different variables. So first graph I want to check is this one. So heat source temperature, I will change it from 30 to 80, and this purple line is 1234 ZD and 1234 ZD. Here we can see if we have the similar one, and here sink temperature we make it constant to 120 degrees Celsius. New, make sensitivity variable 1, and we need to vary the temperature of wait I already had the sensitivity. I will just replace it. Yep, variable 1 we call it, and we need water in. Stream variable water in, we are changing it from 30 to 80 degrees Celsius. We used 6 points, and but we are changing power 1. Power 1 will be compressor 1, and variable of that will be net power. Go with net. Network, that will be output. Power 2 compressor 2. Variable will be network there also in kilowatt, and heat output will be a condenser 2 heat output. Variable will be net duty. Heat will be negative, so you need to make sure tabulate in this, and we go to Fortran also and calculate COP. COP will be heat output, heat divided by power from compressor 1 and power from compressor 2. I use minus because heat will be in minus, so COP won't be in negative. And then we run the model. One more thing, options, and here I will reinitialize all blocks when each case will start. It will not give an error there. Yes, I will save it, and also don't forget to save your models before it will be it will give some errors there. And also now you say the COP will be same. Why is it so? Because we with every source temperature we are cooling it to 25 degrees Celsius at the output there, which is not really the case because COP will depend on this outlet temperature. So instead of keeping it constant, I will make a temperature change of -15. So now if temperature of heat source inlet is 80 degrees Celsius, it will convert into 65, 80 to 65. If it's 70, then 70 minus 15, 55, 60 minus 15, 45, and 30 minus 15, 15. So then the COP will be different. We can see the results. Yes, the results are different. I will put some graphs, results curves. We only need COP. Yes, and then we can also compare with paper values. Yes, so it's all. So at 30 degrees Celsius, paper is showing around 2. This model is showing 1.9, but paper is using different assumptions and using Python programming, and maybe property package will be different. And then let's see, at 40 degrees Celsius it is showing 2.2, and in 40 it's almost 2.3 something. Yep, that's fine. And at 70 or 80 degrees Celsius, COP is around 3.7, and COP is around 3.7 at 80. So that's one thing. So the model is behaving correctly. And if you want to use other fluids, that you can also do. Let's see, we can go back and specification, we can add R134A fluid. Yes, add selected components and R245FA. Yes. Okay, I just replaced it, so I need to add R134A again. Yes. This one is R245FA. Rename. This one is R134A. Rename. Save the model, and now for low temperature cycle we will have R134A fluid, and for high temperature cycle we will use R245 mole fraction. Now you reset it. And the model is giving error. We can see where the error is. Error is in expander 2. So I think if you immediately, the temperature is 88 here, outlet temperature of compressor 2, which is not fine. So we need to change the pressure here. Let's assume here change it to 30 bar. And now I reset the model again. So the critical pressure is different for each fluid, so you need to make sure what you are dealing with different fluids. So that's the only thing you need to do it here. So now the temperature is 93 here, so we need to increase the temperature to, let's say, 35 bar, and then I will reset the values again. Or I think we are using the fluid differently there. Here it should be R245FA, this one will be 0, and there it should be 25. I will keep it, and I will change the fluid R25FA 0 and R134A here. And now we will run it. Yes, I think this is fine now. Yep, and you need to play with it with different fluids and different temperature values. But the model converge, and you can see the COP there also. Simple results. So COP increases drastically. Here, but again I think the fluid selection is important. I will go back 0 there, 134 here, and 1 here and 0 there, and take the compressor pressure to 30 bar, and there I will be, I think this one is fine. And we can see the COP is now behaving a little bit much better, more realistic there also. Yes, and I think this is enough for today's video. It's almost 40 minutes, but if you have any request, if you want to modify it differently, and in next video I can also show why this process is more efficient, why we can recycle here. We can just add a flash drum there and decrease pressure there and take vapor and make this compressor two-stage compressor, and take some vapor back into compressor 2, so then it will be more efficient. And also now you already have the initial heat heat and mass balance, you can convert it into shell and tube heat exchangers there also. So try it, and if you are not succeeding, just tell me, I will do it for you. Yes, and I am also planning to just give these models is a downloadable files.